Hey guys, welcome to the flight dynamics course. Today we are going to discuss about the static longitudinal stability and stick fixed condition. So before that, we have to find out the normal force and clockwise force of the aerofoil. Let us take an aerofoil, which is an angle of incident angle, that is IW, and also has the free stream velocity V infinity. This is the angle of attack alpha. So although for let us consider all the forces acting on aerodynamic center, it will produce lift and drag force. So if you resolve this as normal force and clockwise force, so let us write the normal force N equal to L cos alpha minus IW plus drag of sin alpha minus IW, and for clockwise force C equal to D cos alpha minus IW minus lift sin alpha minus IW. So these equations we have got from the resultant of drag and lift, and also this terms of alpha and IW. So we have derived the normal force and clockwise force in the airfoil. Now we are going to design an airplane such that the placing of main wing, placing of tail wing with respect to CG, that we have to derive here. So let us take a reference plane, that is fuselage reference axis. So we are going to place the main wing and its incident angle IW, and it is the chord line. So we have the angle of attack alpha, that is with respect to free stream velocity. It passes through the aerodynamic center, so it will produce drag will be applied to lift. So again we are taking normal force and clockwise force of wing, that is the and after that we will go. This is the downwash, that is a downwash value, and here we are making the CG from the aerodynamic center of the main wing, that is moment about the aerodynamic center, that is CA. So this is the vertical distance from CG, this is the horizontal distance. Horizontal distance let us take as XCA, and vertical distance is ZA. And now we are going to draw the tail section. So again it will have its own aerodynamic center and tail. So it will also produce some drag of tail, lift of tail, and normal force of tail, and clockwise force of tail. So we have some angle of attack. This angle of attack touches here with the alpha of tail. That is the angle of attack of tail. So tail is also having its incident angle 90. And also tail will produce some moment about tail. So this is the tail of aircraft. This is the wing of aircraft. Tail portion and wing portion, and distance is from the CG, this is height is very is HT, and then horizontal distance is LT. This is the vectorial representation of the main wing placement and tail wing placement with respect to CG. If you want to maintain this wing and tail as an equilibrium, such that we have to take the moment about CG should be in equilibrium. So now we are going to take moment about CG with respect to normal force and the clockwise force, which includes lift and the drag for both wing and the tail section. So now we are going to take momentum for equilibrium condition, taking moment about CG. It is so force into component distance, that is vertical force and horizontal distance, that is normal force into HCA plus the moment about the aerodynamic center, M aerodynamic center B, So we are going to write as tail also. So then we are going to take clockwise force. So this is force into perpendicular distance C into ZA. So this V terms says about where is the main wing from the CG. The V terms will represent the wing. So definitely we will have some fuselage and nacelle other component. Let us take that momentum as momentum about CG for nacelle as well as fuselage. Next for tail. So tail also having force into perpendicular distance, that is clockwise force and LT, that is CT into LT, that is clockwise. That is this normal tail and the XT will be negative. That is a major thing. That is LT into this LT. So here is C3 into H2. C3 into H2. This and plus we have the momentum of tail. Momentum of CG for tail. So these three terms representing the equilibrium vector, force vector and tail. So we have wing contribution, fuselage contribution, tail contribution as a force values. Now we have applying this force into coefficient, that is another dimension number. So we will get the stability criteria. So now we are going to write this force equations as in terms of coefficient. So now we are going to replace this momentum equations as half rho v square this Cm into car is equal to, for normal force, similarly half rho v square SW CL into HCA plus this is a portion of momentum for half rho v square SW CM, this is for wing, CM for wing into this car of wing. The next first term C, that is half rho v square SW CC, that is a guard base coefficient into ZA plus half rho v square SW coefficient of moment for rod fuselage over nacelle plus CT, that is half rho v square tail surface and coefficient of lift for tail and HT is the process minus NTS half rho v square s of tail coefficient of normal of tail into LT plus half rho v square s of wing, that is a surface of tail into chord of tail. So this is the forces of normal force and the clockwise force and momentum force, which representing the interaction of dynamic pressure as well as the momentum coefficient, vector coefficient and drag coefficient. So where Q equal dynamic pressure, that is half rho v square. So now we can get the Cm at the CG will be by removing all dynamic pressure. So we will get CL by XA by C for wing plus that is for CMCG, this CC by C into ZA plus CM CG for wing aerodynamic center, this is for wing term plus CM fuselage plus nacelle plus for tail, that is this entire dynamic pressure is for Q tail. So this is ST, right? So we will get QT by QT ST CLT HT divided by Q of wing, that is Q of wing, S of wing. Right? So this term is over. And again minus for this, again this entire term is QT. So tail dynamic pressure by wing dynamic pressure. Tail surface divided by wing surface. And the LT by chord. Here also it will become C chord. This chord, this dynamic becomes a dimension. And we are getting LT, right? LT plus this term. It is the CM aerodynamic center of tail. So here this tail volume ratio, tail efficiency. This is a tail volume ratio, this is a tail efficiency. This will be indicating from here, from this we are getting the we can replace this HT by CNT. So this term ST by SW plus the tail surface, wing surface into distance of tail by chord is tail volume ratio. Tail efficiency is here dynamic pressure over the tail divided by dynamic pressure produced by the wing. This is the tail volume ratio and tail efficiency. Where here this chord-wise force. Chord-wise force is very small compared with the normal force. Right? This is the normal force. Right? This is the normal lift force. This is the normal lift force for tail. This is the chord-wise. This is the chord-wise force. This is the normal force. So this chord-wise force and here this term that is the coefficient of normal force. So this is very small, so we will neglect this as 0, very small. So again also this tail momentum also very small and we are neglecting that also 0. So finally we are getting the CMCG equation. Finally we are getting the CMCG equation, that is in terms of CMCG. CMCG. Coefficient of moment at CG equilibrium condition, that is CL by XCA by C plus CC by CZA plus CM aerodynamic center wing, right? Plus CM aerodynamic center fuselage and nacelle and minus tail volume ratio, tail efficiency and there is a coefficient of normal force of tail. Right? This is the overall equation which combines which shares the portion of main wing, tail wing, and fuselage portion from the equilibrium equation. This CMCG helps us to understand whether the airplane, designed airplane is stable or not, or which condition, which says the stability criteria. So now we are getting the differential equation of DMCG with respect to CL. If this from differentiating with respect to CL, that is the coefficient of lift, or dCm by dCg with respect to d alpha. So CL versus alpha, we know that if the alpha increases, CL versus alpha for any airfoil or wing condition, it will go up to the stall condition, stall alpha or stall velocity and stall lift coefficient. So these both are interconnected. These two terms, the rate of change of pitching moment coefficient with respect to CG with respect to CL, or the rate of change of pitching moment coefficient with respect to CG or with respect to alpha, should be always less than 0, so that it will maintain the stable condition of the airplane. So now we are going to draw the graph between for CMCG versus CL. So we'll get the CL value. This is the stable curve. This is the neutral curve, and this is the unstable condition. So this CM at CG, portion of momentum at CG, this is for pitch up condition, this is for pitch down condition. So this is we are getting the overall static longitudinal stability equation and its criteria. Thank you. We will see you next class.